Friends, welcome to lecture number 52. So, in this we are going to learn the surface drainage system design 2. So, that means in the previous lecture we were talking about hydrologic design. So, in this the hydraulic design of the surface ditches will be taught. Okay. So, basically in this so what the hydraulic design means? So, it basically refers to calculation of geometric elements of the drainage, the mostly the width and depth and side slopes. So, all these design parameters we are going to estimate by knowing the maximum carrying capacity of the channel. Okay. So, basically these geometric elements of the channel, because open channel. So, this could be like a rectangular channels, or it could be like a trapezoidal channels, or maybe parabolic channels, or semicircular channels. Okay. So, all these different shapes are available, but mostly we will be focusing on these trapezoidal channels here. So, the design geometric parameters are bottom width and depth, and in addition to that we are going to estimate the other information such as stable side slopes. So, in order to avoid the collapsing of the wings, and the channel bed slope in order to maintain the non erosive flow rate, and the channel roughness parameters like Manning's roughness coefficient. So, this is very important in order to avoid channel scouring and having the enough carrying capacity of the channel. Okay, so, the open ditch should designed to fulfill the following criteria. The first one is should carry the design discharge. So, that is the important parameter, that is a bare minimum. So, then should have stable side slopes and also longitudinal side slope for non scouring and non silting velocity. So, we are going to see the procedure how to estimate the design parameters in case of channel design. So, the first step is to estimate the discharge. So, this design discharge is estimated in lecture number 51 using rational method and Cook's method and SES-CN method, the curve number method. So, we can use any of these three methods to estimate the design or peak discharge from the particular watershed or area. And then the second step is to finalize the grade of the channel. So, the grade should have a maximum possible value without exceeding the permissible velocity. So, that is the thing. So, if you increase the grade, what happens, the velocity of flow increases, and that will really scour the channels. Okay. And then the grade should not be so slow, that means so low. So, what happens, so siltation may occur because the flow is not having enough carrying capacity to take out the silt from the channel. So, that will deposit in the channels. So, it does not have any at least the permissible velocity. And the table 1 gives the maximum permissible velocities in non-vegetated canal channels, basically not canals, but the channels for different soil conditions. If you look into the table 1, so this will give the maximum permissible velocities for non-vegetated channels. Okay, so let us see the table 1. So, this is the table 1. So, it gives the first column gives the canal material, let us say the fine sand or sandy loam, silt loam, alluvial silt. So, based on the different soil type, and the Manning's N in second column, and the velocities, this is a permissible or maximum permissible velocities for clear water. So, without having the colloids or the silt, and water with colloidal silts and with the sand, gravel, fragments. So, this is a kind of heavier particles if water contains, then the maximum permissible velocities goes like this, okay, for a particular soil type, right. So, with this table we will be identifying the maximum permissible velocities by knowing the channel material. And the next is so step number 3, so finding out the cross section area. So, for drainage purpose mostly the trapezoidal section is used because it is easy to construct and can be maintained easily. And the cross section of trapezoidal ditch is shown in figure 1 and figure 2. We are going to is in the next slide, gives the stable side slopes for open ditches. Okay, so, and the size of the ditch can be determined using Manning's formula. So, once we know the channel geometry or decided the channel cross section, so then we will be using the Manning's equation V equal to 1 by n r power 2 by 3 s power half by knowing the Manning's n and knowing the permissible velocity V. See, unknown parameters which are plugged in R and R, not S, S is known in M. So, unknown parameters like geometry parameters R will be estimated. So, you see the table number 2, so in which the side slopes are given, the side slope for a particular channel. So, here the soil type, if it is a peat and muck and stiffy clay and clay and silt loam, sandy loam and loose sand, for all these soil type, the shallow channel, suppose you are planning for shallow channels, that is less than 120 centimeter deep, with a deep channel, so greater than or equal to 120 centimeter deep. So, the vertical and horizontal slopes are 0.1:1, 1:1, 1.1:1, 2:1 for the different soil types. Similarly, you can find the side slopes for deep channels. Okay, so here this is the trapezoidal channel. So, for trapezoidal channel it has a parameter B, the bottom width, and depth D. Okay, so, and then we need to include a freeboard in order to accommodate if there is a siltation or other things. Okay, so generally the freeboard can be up to 20% of D. Okay, I mean this is extra. So, that will be, and once we put the capital D, you can find out the top width according to the capital D. So, capital D which is equal, let us say if the maximum is 20%. So, that is a 1.2 times D. So, knowing the capital D, you can update the top width accordingly. And there is a berm. Berm is it is also like a spoil banks. So, spoil banks are very important. So, this will help in controlling the collapsing the side slopes and other things. So, the excavated earth from the open ditch may be placed on one or both sides. So, whatever the excavation you are taking, so this will be kept on one side, and the berm width should be minimum 3 meters. So, this is at least minimum 3 meter we expect the berm minimum width are shown, and spoil banks should be provided with flat side slopes of 3:1 on channel side and 4:1 on burned side. So, this is the burned, right. So, this is the burned, and then channel side. So, this is the channel. So, this is the channel and this is the burned. So, the spoil banks will be provided with flat side slopes at 3:1 at this side, and then little bit of flat side slopes here. So, that will be 4:1 on the burned side, okay. Sorry, channel side. Okay, so, here is an example in determining these geometric parameters of trapezoidal channel. So, let us see determine the efficient trapezoidal section of drainage ditch required to carry a peak runoff of 1.4 meter cube per second. So, this number we got from using any rational method or SES curve number method or Cook's method. And then the channel is constructed in alluvial silt. So, this from the table we can get some information on maximum permissible velocity and also Manning's N. So, the bed slope may be assumed 1 by 3000 approximately as per topographical conditions, existing topographical conditions. So, the solution here is using continuity equation Q is equal to A into V, where V is Manning's roughness Manning's roughness equation, that is 1 is equal to 1 by n, V is equal to 1 by n r power 2 by 3 into s power half. So, substituting in Q, so A into V, so then A into A r power 2 by 3 will be taken out, and Q n by square root s. So, this from table 1 from alluvial silt n is equal to 0.2. So, substituting the values like 1, this is Q and this is n, and you get A r power 2 by 3 is 1.5336. So, we will carry forward that in the next slide, the remaining calculations from table 2. Now, side slopes for for these kind of soils, alluvial soils, is 1.5:1. If B is the bottom width and D is the depth, so now top width is equal to B plus 3D, because it is 1.5. So, B plus 2 times 1.5 times D, so that will be B plus 3D. And wetted perimeter P is equal to P plus, so wetted perimeter, so this is B, right, and then you have to find out the length of this shoulder. So, that will be so this is 1.5 D, and if this is D, so this will be D square plus 1.5 D square and whole square. So, that will give so because again the 2 times including this side. So, this plus this plus this, so that will be B plus 2 times of the side slope, side length. So, that will be P. The substituting, simplifying this, you get this this equation, and then P is equal to B plus 3.606 D. So, this is the perimeter. Now, A is equal to so this is trapezoidal equation. So, B plus 3D into D by 2. So, this basically for trapezoidal channels. So, area of cross section for trapezoidal channels, so will be so this is one triangle, another triangle, and then this is B and this is D. So, 2 triangles here and one rectangle. So, B into D plus half 2 times half BD. So, this will be 1.5 D, 1.5 D into D, right. So, that will be B into D. So, that will be B plus 1.5 into D. So, now hydraulic radius R is equal to A by P. So, that will be R is equal to A by P. So, substitute for A. So, A you get from the previous from here you get, and P. So, this is from P. So, now substituting A r power 2 by 3, which is equal to 1.4 into 0.02 divided by square root of. So, this is from the previous slide, and then 1.5336 from previous slide you get, and therefore, you can substitute this A r power 2 by 3. So, that is substituting this A, this is A, and R power 2 by 3. So, this is A and R. So, this is 1.5336. So, after simplification, okay, you can still keep it, but here for side slopes we know 1.5:1. So, that is tan theta. So, tan theta in the sense, so here this is the theta, okay. This is theta, and you have, so this is the theta. So, vertical is 1.5 and horizontal is 1. So, that will be tan theta will be 1 by 1 for, oh, okay. So, this is the theta, this is theta. So, 1.5, sorry, this is theta. So, just a minute. So, tan theta is equal 1 by 1.5 because so 1.5 is to 1. So, if this is the theta, right, and this one is so this is d, and this is 1.5 d, okay. This is 1.5 d, and this one is 90 minus theta, right, 90 minus theta. So, now we can estimate, you know, tan 90 minus is the cot theta, and then you estimate the theta value. This is the slope, okay. This is the slope, and theta will be now for tan theta by 2 will be 0.3038. So, for efficient section, so this B is equal to 2D tan theta by 2 is the efficient, you know, efficient is the most economical channel, I mean trapezoidal channel equations. So, we discussed this in the previous lectures when we were talking about you know, the most economical channel depth and width relationship. So, that is 2D into tan theta by 2 0.3028. So, that will be 0.6055 d, and substituting this value in B, okay. So, B is value of B in this equation. So, this equation that is A r power 2 by 3. So, from the previous slide. So, now if you can substitute B value, and finally D will lead to D equal 1.091, and now B is equal 0.6055, and that will be, let us say, 61 centimeter, okay. And then now we are checking the velocity, r is equal to A by P. So, this will be r value, and V equal to 1 by n r power 2 by 3. So, substituting the given or estimated values, we get 0.609 meter per second. And if you go back to the tables, right, I mean table number 1, you see 1.05 meter per second is the maximum permissible velocity. So, this velocity is less than this, so within the permissible velocity. And finally, the geometric parameters for the trapezoidal channel, or bed width is 61 centimeter and depth is 1.3 meter. So, that including 20% of freeboard, and side slopes 1.5 east 1. Okay. So, this way we will be designing the parameters for cross section, trapezoidal cross section. So, now another example. So, find the section dimensions of the drainage channel to carry runoff of 50 hectare watershed with a drainage coefficient of 5 liter per second per hectare. So, each 1 hectare land will lead to 5 liter per second runoff. The given parameters are channel bed slope is given as 0.2%, channel side slope z equal to 1, maximum permissible velocity 0.6 meter per second, and Manning's roughness coefficient, that is n equals 0.025. So, the design discharge area into drainage coefficient. So, that will be 50 hectares and 5 liter per second per hectare. So, that will give 0.25 meter cube per second. So, from Manning's equation, so this is the Manning's equation, and so substituting the given values like n, s value, and also there is a V is given. So, substituting except R, substituting the values, so V equal to 1.7 and R power 2 by 3. So, that will be so this is the V, and now R power 2 by 3 will be V by 1.79. Substituting V value, you get R is equal to 0.19407, okay, this is in meters. From continuity equation, Q equal to A into V. So, where A equal to Q by V, and you get this is A is in meter square. So, also now A, so B D into Z D square, this is area of cross section for trapezoidal channel, or B into D into Z equal 1 D square, and now area from here and B D plus D square. Now, so this is the previous equation, B D plus D square is equal to 0.4167. Now, B is equal to this much, and R, since R is equal to A by P. So, A equation and P equation. So, now substituting B in R, and now R equal to 0.1947, this is we estimated previously, and substituting the values which are known, for example, like B value, substitute the B value in this equation. Okay, so that you get the B, this is B value, and D plus 1 by D square plus, and like that. Now, again simplify a little bit. So, after simplification, okay, so you get a quadratic equation in D, D square minus 1.1746 D plus 0.22796 is equal to 0. So, it has two roots. So, one is minus 0.477 and 1.434, this is positive and negative. So, so since it has two roots, so sorry, it has two roots, that is 0.9269 and 0.2477. So, substituting the one root, okay, into this, so that will be, and you will get B is equal to, so D has two roots, okay. So, D has sorry, so D has two roots here. So, one is sorry, yeah. So, substituting D is equal to equation, so substituting D is equal to 0.9269. So, you get minus 0.477, substituting 0.2477 here, you get 1.434. So, since it is negative, so the root I mean D is equal to 0.92 is not the correct one. So, we have to take D is equal to 0.2477 because it is giving the positive value. So, the first root is not feasible. Okay. So, and now B equal to 1.43 and D equal to 0.477 meters, that will be 24.8 centimeter. So, and then the flow area, so that is 1.43 into, so substituting the equation, so 0.416 meter square. So, now we got the flow velocity, that is equal to the flow velocity Q by A. So, that is a 0.6 meter per second. Adding freeboard 5% depth to the design. So, since the depth is 24.8, so into multiplied by 5 by 100, you get 26.04 centimeter, or say 30 centimeter. Now, top width B plus 2 into ZD, so that will be 2.03, and the cross sectional area B d z d square, so this much. So, now volume of earthwork per meter of length, so with drainage will be, so area multiplied by 1 meter, so that this is the volume of earthwork, I mean that will be 0.519 meter cube. Okay. So, this way you can estimate the geometric parameters of the trapezoidal cross section or ditch. Okay, so in this the main design. So from hydrologic design you will be knowing the Q value. So in hydraulic design, so knowing the Q value, you have to assume, so mostly the trapezoidal channels will be used for designing the drainage ditches. So knowing the Q and permissible velocity and based on the based on the soil type, so and the corresponding roughness coefficients in table number 1. So you will be estimating the channel dimensions. Okay, so then if the slope is not given, so you have to assume, or you have to take slope for a particular soil type from table number 2. So using this information you will be able to estimate the channel dimensions like breadth and depth and also the top width, if you can put maximum 20% as a freeboard to avoid any siltation in the channels. Okay. So with this I think we finished both hydraulic and hydrologic design in case of surface drainage systems. So thank you.